Rahim. This is Jahangeer Soomro, Assistant Professor and Principal Investigator of Hardware and Loop Laboratory at Electrical Engineering Department, Sakkara University. Today I will present the summary of one of my research paper, Efficient Real-Time Controller Design Test Bench for Power Converter Applications. In this paper, we will discuss how can we best utilize hardware and loop setup for research in the domain of power converters. Basically, the first thing that we need to understand is that the simulations that we perform on computer are called offline simulations. We use different software for software simulations or computer simulations like MATLAB, PSIM, PSCAT, LabVIEW, or any other software. Now, offline simulations or computer simulations are extensively used to investigate the performance of electrical system or power converter due to its minimal cost and less efforts. But the problem is that offline simulations or computer simulations do not replicate the actual or real behavior of the power converter. Therefore, engineers and researchers cannot fully rely on the offline or computer simulations. To overcome this problem, engineers and researchers use hardware and loop setup to get real-time simulation results. Real-time simulation results, as opposed to offline simulation results, offers deterministic and results closer to the experimental results. It means that real-time simulation results represent the actual or real behavior of the converter. See here. Now we can clearly see that the results of the Hill simulation setup, hardware and loop simulation setup, and physical system setup are very similar. So this is the advantage of Hill simulation setup. So Hill is basically best fit for early validation of power converter before its final deployment or final implementation. So in the planning stage, you can validate your converter and controller in fill to save time and enhance the quality of the project. And after that, once you get the results on the Hill setup, you can move to its physical system prototype. All right. Now let us discuss the abstract of this paper. In order to evaluate and validate the latest trends of hardware and loop setup, the DC to DC buck converter is modeled with a real-time system where the simulation model of the converter is exported to FPGA NIPXI with a real-time step of 259 nanoseconds. Now here I would like to clear one thing, that you will design and model the power converter using these four softwares in our proposed hardware and loop setup. You may design the power converter either by using MATLAB Simulink or Plex or PSIM or Multisim. All these four softwares are supported in our hardware and loop setup. And without the need of any VADL programming or FPGA expertise, you can directly load after designing the power converter in these software into NIPXI. So it will automatically generate the code using this EHS software. This is the beauty and advantage of this hardware and loop setup. So this thing should be clear that converter is basically simulated, but it will run in nanosecond time step and it will replicate the actual or real behavior of the power converter. Alright. Fill setup allows high flexibility, the benefit of graphical programming and advanced investigation of control system for a converter without any safety concern, with the possibility of testing against situations that rarely occur in the field. Alright, now we should understand that mostly the power engineers do not learn text-based languages such as Verilog and VADL to program FPGA. Now, using this efficient hardware and loop setup, you need not to be expert or familiar with VADL or Verilog. You can design digital controller for the power converter using high-level language, that is LabVIEW. So, controller will be designed using LabVIEW. Alright, and as already discussed, that your converter will be simulated, so there is no fear of failure of the switches or other components of the circuit. So extreme digital controller testing can be performed for different scenarios without any fear of damage of components, because the converter is simulated and the controller is real or physical. And therefore this setup is also sometimes known as controller hardware in the loop, chill. Alright. The LabVIEW FPGA has been used as a prototyping environment for digital controller with the help of OpalRT, EHS software and NI hardware. Such collaboration enable other software such as MATLAB Simulink, Multisim, Plex, PSIM and LabVIEW co-simulation for accelerating innovative research and development. Now, the distinctive feature and fundamental beauty of this platform is that basically researchers and students at first start with offline simulation results. They design their controller in NI LabVIEW, they design their converter of the controller, the converter in NI Multisim. And utilizing the key benefit of Multisim LabVIEW co-simulation, they can test and validate the behavior and performance of their converter using the computer facilities. Once their converter and controller works fine and gives satisfactory results, then with some minor modifications and changes, the same LabVIEW code can be deployed in either Myrio or Serio controller, and the same multi-sim circuit with some minor changes can be deployed in NIPXI to get real-time simulation results. So the journey from offline simulation results to the real-time simulation results become easier. So this is the main advantage of this hardware in loop setup. Alright. Moreover, circuit can, other than multi-sim software, the circuit can be designed using MATLAB, PSIM or Plex. This research work presents a more efficient and effectual NIPXI platform with at least 10 times more FPGA capability. This paper highlights the hardware-software toolcell performance and the proposed methodology by addressing regulation issues in DC to DC converter. For more satisfactory and reliable operation, the real-time simulation study of a DC to DC buck converter evaluated a different parametric variation under a closed-loop PI controller. Now, it should be noted that this setup can be used for research in any of the advanced converters, but in this case DC to DC converter is taken as a case study. Like in one of our research paper, we have used the same platform for proposing reconfigurable power quality analyzer, and in 3 of these research papers we have proposed advanced and enhanced modular multi-level converter MMC for HVDC application using the same platform. So this platform is open access platform and any type of power converter study can be performed in such setup. Finally, the executed model effectiveness for a closed loop buck converter with a real DC load is validated through the hardware and loop laboratory setup. So finally, we have also placed the real DC loads like as shown here. The real DC loads are tested and the converter behavior is tested on real DC loads. Moreover, we have also compared the results of our hardware and loop setup with physical setup to validate that the obtained results are very close to the experimental or physical prototype. All right. So this is our laboratory setup. We see results on these screens. We have two such hardware and loop setups at our laboratory at Sakkara University. This is NIPXI. These are two stereos. This is power amplifier. So in this case, the controller is deployed in stereo and the converter is simulated and deployed in NIPXI is discussed already. So this is working in the closed loop. Also we have obtained results for software and loop setup. In software and loop setup, both the controller and the converter operates in simulated mode as shown here. This is the rapid control prototyping digital controller for our DC to DC converter that is deployed in Myrio and that can be also deployed in stereo. This is a buck converter. Input voltage is 200 and it is stepped down to 150 volts and the behavior is tested for different values of Kp and its results of hardware and loop setup are compared with software and loop setup and we can see that the results are almost similar. Here for different values of Kp, the results are repeated. If the Kp value is not properly selected, we can see oscillations and disturbance here and this is unwanted case and this may damage your converter. So avoid choosing very high values of Kp that can damage your converter. This shows how robust our proposed setup is, that if you change the reference voltage from 150 volt to 130 volt within the few milliseconds, it tracks the new reference voltage, so it is very fast. Here it is shown that if the input voltage changes from 200 volts to 180 volts, again the system is very robust and it tracks the new change in a few milliseconds. Also, when the load resistance changes, the converter and controller can track the reference voltage very quickly. Finally, as discussed, we have compared the results of our hardware and loop setup with physical prototype. This is a physical setup. Now the converter is deployed in stereo and this is real physical controller. The controller is deployed in stereo and this is real physical controller. Also, we have replaced the simulated circuit that was initially operating NIPXI with the physical prototype of the physical buck converter. So this is physical and experimental setup, and we have compared the result with the hardware and loop setup. So in this figure we can see that the results for the hardware and loop setup, for our proposed laboratory setup, and the experimental physical prototype setup are very similar. The results are repeated for different switching frequencies, and in the table it can be seen that hardware and loop and physical prototype setups results are very similar. So our proposed laboratory setup is validated with the physical system. Thank you very much for listening. If you are interested to listen more videos in the field of power electronics and hardware and loop setup, please subscribe my channel. Thank you very much.